Hi, class. Today we are continuing with chapter 9. So there's two parts to this lesson today. The first is systems of equations, and the second is the intersection of two planes. Okay, I think I might make this into two videos. We'll see how I feel partway through. So in the last video, we learned about elementary operations and how we have used them to solve a system of two equations in the past, so just a linear system. Today we're going to use elementary operations to solve a system that has three equations with three unknowns. So this is a nice little step in your mathematical journey. So the solution to a system consists of all values of variables that satisfy all the equations in the system. We can use elementary operations to create equivalent systems, which get progressively easier to solve. So when you have two unknowns, you need two equations to solve for those unknowns. And when we have three unknowns, we require three equations to solve for those unknowns. So we're just going to basically get started and dive into an example. I think the best way to learn this is just by example, doing it over and over again. And basically, it's going to be a lot of fun, I think. Okay. So here we have a system, and the very first thing that we're going to do is label equation 1, equation 2, and equation 3. Okay, so this system consists of 1, 2, and 3. So we're going to make alterations, add and subtract equations to come up with our solution. So the first thing we want to do is eliminate a variable from two of the equations. So we're going to eliminate x in equation 2 and in equation 3. And I'm going to use equation 1 in both cases. Okay, so I guess using equation 1. All right, so we're just going to use elimination. So I'm going to multiply equation 1 by -2 so that when I add it to equation 2, the x's eliminate. So -2x plus 2y minus 2z equals 2. Oh, -2, sorry. My biggest mistake is I often forget to multiply that last number. So that's just something to be careful for. And then I'm going to add equation 2. So I just copy it out. As written. Okay. And so when I add, the x's are eliminated, which is the desired effect here. So I get 3y minus 3z equals, that should have been 11, sorry, equals 9. So I'm going to call this equation 4. So it's a new equation created by these. Okay, I'm going to do something similar then with equation 3. So now I have to multiply equation 1 by equation. This is not an occasion, equation. Equation 1 by -3 so that when added to equation 3, I can eliminate the x. So -3x plus 3y minus 3z equals -3. And I'm going to add that to equation 3, which is 3x plus y plus 2z equals 12. And now I'm going to add them together. Notice the x's eliminate. So I get 4y minus z equals 9. And I'm going to call that equation 5. So now the new system that I'm trying to solve is equation 1, equation 4, and equation 5, okay? So 2 and 3 have been altered, but the system 1, 4, 5 is an equivalent system to 1, 2, 3. So now my next step is to eliminate a second variable from one equation. So I'm going to eliminate y from equation 5 using equation 4. So I need to multiply equation 4 by -4/3 in order to get a coefficient so that the y's will eliminate. So I'm going to multiply equation 4 by negative 4/3. So I get minus 4y plus 4z equals negative 12. Then I'm going to add that to equation 5, which is 4y minus z equals 9. So again, the reason why I chose negative 4/3 is because that gave me a coefficient on y of negative 4, so that when I add these two, the y's eliminate. So then I get 3z, equals negative 3. So this is equation 6. Okay, so now I get a new system, equation 1. Okay, so now I could take equation 4, but something that we often do, it could be 1, 4, 4, 6 is what I could do. I could do 1, 4, 6, but at this point, I'm going to scale equation 4. So it is just y minus z equals 3. Okay, and then I'm going to call that equation 7. All right, so I've just divided the entire equation by 3. So because I am dividing the entire equation, I'm allowed to do that. So 1, 6, and 7 is my new system. So now we use something called back substitution. So notice that looking at equation 6, I can solve for z. So z is equal to negative 1. That's from equation 6. Now I'm going to put that into equation 7, which only has y and z, to solve for y. So y minus negative 1 equals 3. So y equals 2. And then I can put that z and this y back into equation 1. X minus 2 minus 1 equals 1. And solve for x, which equals 4. So the solution to this the solution to this system is 4, 2, negative 1. So this is the coordinate that satisfies all 3 equations. So if you use left side, right side with all 3 original equations in the system and subbing in our x value of 4, y equals 2, and z equals negative 1, all 3 equations will achieve left side equals right side with that given coordinate. So essentially what we're doing is using elementary operations to create this lower triangle of zeros. So we want one of our equations to have all 3 variables, one of our equations to just have 2, and then our last equation to only have 1 variable, so we can solve for it. And then, like I said, it's called back substitution, back substitute up until we get all 3 variables. Okay, so try this, solve this system. If you're really brave, you can try it on your own if you really want to, or you can see if you can do any of the steps on your own. Okay, so remember the first step is to label these 1, 2, and 3. Okay, so step 1 is to eliminate 1 variable from 2 of the equations. So in this case, I'm going to eliminate z from, what do I say here? 2 and 3. You can really do it in any order, okay? You can change the order, but this is what I'm going to do. Because see, z is just a coefficient of 1 here in equation 1, so it's easy to alter equation 1 to get the desired coefficient to eliminate z in both of the other equations. That's why I do that. But really, you can reorder the equations before you start, and just leave the one that you're using to eliminate the others at the top is usually the simplest way to do it. So to eliminate z in equation 2, I need to multiply equation 1 by negative 2. So negative 4x plus 6y minus 2z equals negative 12. That last number, I almost did it again. And I'm going to add that to equation 2, which is x plus. Okay, and when I do this, I get minus 3x plus 7y equals 19. And that's equation 4. And then notice I just have to add 1 and 2 together here. And when you do that, you're going to get 3x minus 5y equals negative 11. And that is equation 5. So I got that just by adding equations 1, and 3 together. Okay, so my new system now is 1, 4, and 5. I like to just always keep my head around what I'm doing and actually say that. You may or may not find that necessary. It's not required to say that. I just find it keeps me organized. Okay, so now I'm going to eliminate x from equation 5. And this is rather simple because I just have to basically add 4 and 5. Okay, so you can eliminate them in any order. You kind of just want to pick the path of least resistance. So this gives me 2y equals 8. So this is equation 6. All right, so now I can solve for y. So y equals 4, and now I can back substitute, okay? So I know that minus 3x, sorry about that, let me just rewrite that. Minus 3x plus 7y, so 7 times 4 equals 19. So when you solve this, you get x is equal to 3. And then you can go, so here I have x is equal to 3, y is equal to 4. And if you put those back into equation 1, you get 2 times 3 minus 3 times 4 plus z equals 6. So then you can solve z equals 12. So your solution then is 3, 4, 12. Just make sure you write it in the right order, x, y, and z. Okay, so I would encourage you now to go to page 509, number 12b, and try that one just to see if you're able to do it. It's a good little self-assessment to see if you've understood this process. So I'm going to do a separate video for intersection of planes just to keep them separate. So thanks for watching, guys. Hope you learned lots.